Hello everyone, this is the video for section 15.2, which is on displaying data and interpreting data displays. So in section 15.1, we talked about what data is and the different types of data. And so now once we've collected all that, it's going to be helpful if we can present it in a way that allows us to see a larger picture sort of all at once. In the case especially of a larger data set, just presenting somebody with a large data set, it's a lot to take in. So using some sort of pictorial representation or some sort of organized graphic representation is going to help in presenting our data and allow people to understand what's going on a little bit easier and clearer. So that's what we're going to be looking at in this section 15.2. So let's get started. So the way I've organized this is sort of the way that it's organized in the book. And so in the book, it goes through first categorical data displays. And again, if you're not wholly clear on the difference between categorical data and numerical data, you might want to go back to section 15.1 and read that section of the book or watch that video again, that part of it, and make sure that you're clear on the difference between the two. Because understanding the difference between those two types of data is going to be important to understanding how these graphs work. So these first graphs that we're going to look at are all going to be categorical data displays. And so the first one that we have here is this thing called a real graph. And a real graph, I mean, it's what it looks like. It's a real graph. It's a graph that uses real objects. And so sometimes you'll see this referred to as an object graph. It's mentioned that in the book, and online you'll see this referred to as an object graph as well. We're using the actual objects to construct the graph. And so you can see that this classroom example, the question was, well, what kind of shoes are you wearing? Are you wearing shoes that have Velcro, that have have shoelaces that have to be tied up, or that are slip-on? And so what's making the graph are the real objects themselves. That's the real part of the real graph. We're using the real thing. Now, this has its roots in uh, educational theory that you'll hear a lot about, and that's this sort of continuum between concrete and abstract. And so concrete is when we're working with a physical, tangible object. And then abstract is when we start to move that into something else. We start to move it into symbols or pictures, but we're drawing meaning from the actual object. This is about as tangible and concrete as you can get. We want to make a graph about shoes, so give me a shoe, and I'm going to make a graph using your actual shoes. And so this movement from concrete into abstract, you'll hear about in other math education courses and in other education courses, and we're going to hear about it a lot as we sort of move through this progression of graphs. So that's what a real graph is. Actual objects, actual things, making the graph out of what we have. So now you can see this little bit of an abstraction. And so this graph deals with what's the favorite fruit of students in a class. And so we've got little smiley faces that represent a vote, and we've got 10 votes for apples. Now, if this were a real graph or an object graph, we might say, okay, well, what fruit did you bring with you for lunch today? If you have an apple, put an apple on this thing, and you would use the actual apple. But there are no real apples here. So you can see how this is an abstraction. That smiley face represents really a vote for an apple. And we can't put a vote on a thing because it's not a tangible object. So we can't put a vote on a graph or a piece of paper. So we use this picture to represent something. So it's not literal anymore. We have something that is an abstraction or a representation. And so now we're going to count up 10 votes, 7 votes, 2 votes, 6 votes. So now we know how many votes there are for each of the different fruits. We still have one symbol representing one thing. We still have a very concrete picture of this. We can tell how many there are just by counting. So it's still very concrete, but more abstract than actually putting shoes on a piece of giant graph paper and constructing the graph that way. So this is a pictograph, a graph that's using pictures to represent items or elements or ideas in a graph. So now we have a bar graph. And so now we see here our quantities of fruits sold. And so we've got our fruits along the x-axis, apples, oranges, bananas, kiwis, blueberries, and grapes. And then our y-axis is how many of those were sold in kilograms. Again, if this were a real graph, we might actually have apples, oranges, bananas stacked up to represent what these are. But you can see that because the y-axis is the amount in pound or in kilograms rather, that it's the weight or the mass of the objects, having them stacked up kind of loses some idea of why we would want to do that. It's not how many shoes that have Velcro are in the room, where now that makes sense to take the actual shoe. The y-axis is becoming a little bit more abstracted because how do we represent kilograms of something? So the actual object doesn't represent the kilogram. Now, if you had all apples and each apple was 1 kilogram, first, that's a giant apple. But second, you would have to find a whole bunch of those in order to do that. You'd need to find 35 apples like that. So it becomes unwieldy to use that real graph to a certain point. That's a motivator to moving into this abstraction, that we're dealing with either an X or a Y, sometimes both, where the abstractions is going to make it that much simpler. And you can see the abstraction from the pictograph because that apple bar of 35, there's not 35 individual objects. We've taken the 35 apples or smiley faces or whatever it is, and we've abstracted that into a bar. And now the length of that bar is going to represent how many we have. So hopefully you see this evolution where we've gone from actual objects to pictures that represent the objects to now this one object that represents multiple objects. So you can see this abstraction as we go along. Students can now look at the x-axis and see which category it is, look along the y-axis, and see how many there are in each of those categories. And so this is a bar graph. I do want to point out the bars don't have to go up. A lot of times they'll go up, but it's not uncommon to see a bar graph where the bars go left to right or even right to left. So it's a little confusing if students are learning this for the first time because now you're playing a little fast and loose with X and Y axis a little bit. So my recommendation would be doing this for the first time. We want to do all of these with the X and Y axis consistent. And then once students become comfortable and fluent with this idea, now you start to look at different representations of these graphs. This is a double bar graph. And so this double bar graph now is what it sounds like. We've got two bars that represent different parts of the same idea. Let me explain. So this data represents the end of the season, the English Premier League, how many points each team has. And so you can see up at the top, that bar is for Leicester City. And so their total points would be the red bar and the blue bar combined together. But we can separate this out now to show the red bar is how many points they scored at home, and the blue bar being how many points they scored away from home. And so now we can tell three things at one time. We can tell the total points, we can tell the points at home, we can tell the points away from home. We go down, we can see each of that for each of the teams. So by using the two bars, we can embed more information into what's going on. It's just using the bars in a slightly different way. You'll see these a lot of times, multiple bar graphs where you'll have, say, male and female, or white versus person of color, or whatever, when we have a lot of different demographics that need to be displayed at the same time. So this is a very common graph to see like this. We have a pie graph. Favorite pizza toppings: pepperoni, cheese, sausage, supreme. And so now we can see there's a little key to the right. So we know that the green piece is the pepperoni piece. This purple is for cheese. This yellow is for yellow orange, which is for sausage. And then that brown for supreme. This is much more of an abstraction now because these are proportional to some sort of whole. And so we don't know how many pepperoni or how many people have pepperoni as their favorite pizza topping. We can't tell the actual raw number. If you think back to the very beginning, we could count the number of shoes. We knew how many students had shoes with Velcro. Here, I don't know how many students prefer pepperoni, but I do know that it's half of the total class. So now this percentage becomes an abstraction which makes this a little bit harder to understand, and yet also gives us a different layer of information all at the same time. So this pie graph as a circle, a lot of times as a circle, is going to show percentages. Now we could, if we wanted, uh, do this as, say, we had 100 people and we've got 50 people here, 25 people here, 15 people here, 10 people here. So in that case, we've got the raw number which directly correlates to the percentage. So you will see sometimes pie graphs like this that show the raw data in addition to, or sometimes even instead of, the percentage, but most of the time you'll see the percentage incorporated into this graph somewhere. So now we're going to move on to numerical data displays. And so again, like before, if you're still not entirely sure about the difference between categorical and numerical data, you may want to go back and look at it. But these graphs will all be dealing with numerical data. In a lot of cases, you will see graphs that look very, very similar. In fact, this first graph, which is our dot plot or line plot, and we're not going to use line plot an awful lot for reasons that will become obvious here in a moment. But this dot plot should look a lot like that picture graph where we had the smiley faces representing a vote. Because again, we're using a dot to represent uh, the number of somebody who has a certain number of hours slept. So we can see how many people slept for 7 hours. Well, 3 people. And how can you tell? Because there's 3 dots. Now, those dots could represent 10 people or 1,000 people or 1,000,000 people, but we'll assume for the sake of this example that each dot is one person, say, in a class. That person sleeping 12 hours, I'm so jealous. I haven't slept 12 hours since I was probably an infant. But anyway, you can see how this is very similar to a pictograph. And this is a really important point. Sometimes when you look at a graph like this, it's really hard to tell exactly what type of graph it is without first identifying what type of data it is. If you just saw this graph without any of the words or any of the numbers or any of the anything, it would be almost impossible to distinguish it as a dot plot showing numerical data versus a pictogram showing categorical data. So making sure that you can tell the difference between those two types of data is going to be crucial to being able to determine what type of graph you're working with. Here's our histogram. Again, this is the numerical version of a bar graph, which would show that categorical data. And again, we can see our male employee height here, 5'7", 5'8", 5'9", 5'10", and then going down. I mentioned this in the 15.1 video. Well, what do you do if somebody says, well, I'm 5'9.5", or I'm 5'10.25"? So this numerical data gets a little bit weird because we're effectively constructing almost categorical data because we're putting things in these sorts of categories. So again, we want to think about how we're recording the data, and then we might take somebody who's 5'10.5" and just say, you know what, we're just going to count them as 5'11", or we're just going to make them 5'10" to make the data work out a little bit easier. But it's a little bit of a gray area there in how you manage and handle and record that numerical data, that you don't treat it too much like categorical data and that you don't wash too much of the meaning out of the numbers. But as far as the graph goes, you can see that it's operating very, very, very much like a bar graph that we looked at earlier. Stem and leaf plot takes a little bit more explanation because it's not really pictorial in the way that we might think. Each of the numbers on the right of the line represents the unit of a two-digit number. So you can see this 4 and 1 up at the top. So you can see this 4 and this 1. That together makes a 41. Now below that you can see a 5 with a 2, 7, and 8. Those are all numbers in the 50s. So that would be 52, 57, and 58. Likewise, down here, this number would be essentially 65 and 66. So we can fill these things in here. And so since this 50 part is common, we just sort of put it out here, almost like the distributive properties, like we're distributing out the 50. It can be a little confusing for students because understanding this 5 is a 50, and as much as you might want to write it as a 50, please don't, because students who have seen this before are now going to read this as 502. So we want to make sure that we use sort of a consistent representation of stem and leaf plots. So when you have data that's kind of bunched up together like this is a really common way of representing that data. If you have a whole bunch of data that's really condensed and centralized, sometimes you'll see like this 7 broken into 2 categories. So you may have the 5, the 0 and the 5, and then the 8, 8, 8. So you've got 0 through 5 and then 6 through 9, or you could do 0 through 4. Split that up into 2 sort of subcategories. So that stem has 2 different subcategories of leaf. So you will see that sometimes to prevent one category from going on sort of way too far. You can see how the distance to the right is very similar to the bars in a bar graph or those bars in the histogram that we just looked at. So there's still something to see in terms of magnitude and distance and height, in this case, that distance to the right. So here's our line graph. And this line graph is why we're not going to use line plot for that dot plot earlier, because the names are very similar, but they represent very different things. You can see here what's happening. On Sunday, we've got this value of 25. Sunday we get 25, Monday is 15, Tuesday is 25. Now, in this case, what does this line really represent? Did I do 20 push-ups at midnight between Sunday and Monday? No. Only this point has meaning and this point has meaning. But now these lines are here to show movement. They're here to allow us to notice patterns or to do some type of inference that we'll talk about here in a moment. So again, this is a lot more of an abstraction because we have things in the graph that we effectively don't really need. They're not literally representative of anything in our data other than to show trend or pattern or movement. So this is what we have by a line graph. The last one we're going to look at is this thing called a scatter plot. And so in a scatter plot, we've got 2 different variables. So here we're looking at height and weight. And so this dot here is going to be some ordered pair of height and weight. So let's say that this is somebody whose height is 63 and whose weight is about, let's say that looks like about 137 roughly. So we would collect this data, excuse me, what's your height, what's your weight, in whatever units this is supposed to be. I don't know, the height is in meters and the weight is in metric tons. So whatever we measure it in, we get this, we collect this data, and then we find this point and plot it to represent these 2 values. So this allows for a lot more variability both on the x-axis and the y-axis. We're moving into a lot more continuous form of sort of data. You can see here if we were asking for people and they gave us their height as say 62.5, we don't have the same problem we had with the histogram where we got to make a new bar. I could just put that dot in here somewhere and it fits with the data just perfectly. So this is very flexible, very malleable in the way that we can collect and store the data, but the trade-off for that is that it's much more abstract. For students that have never seen this before, it's just a bunch of dots. So there's going to be some work getting them to understand what's happening in this graph. So the last thing I want to look at is the levels of student graph comprehension. And this is mentioned in the book on page 689. Yeah, 689. And this is from the Curcio article from 2001. And in the back of the book, there's the full citation if you want to read this actual full paper. And what we have here are 3 different levels. And so the first level is just reading the data. And it's exactly what it sounds like. You're just literally reading values off of a graph. How many students did this? How tall was this person? Whatever it is, it's just literally taking the values from the graph. So you can think of this as, using the Bloom terminology, is just knowledge. Do students just have knowledge about how graphs sort of operate? The second level is reading between the data. And now what this means is, can students do interpretation or even interpolation and comparisons about the data points? So do we notice a pattern? What do we notice happening from here to here? In the last graph about height and weight, as someone gets taller, what do we think is going to happen about their weight? Does someone weigh more or weigh less the taller they get or the shorter they get? So now we're sort of making comparisons between there. The last one is reading beyond the data, and that's making predictions and inferences about the data. And so now we're moving into analysis and synthesis from the application really of the second level. Now, can we really start to make larger inferences about what's going on? And so if somebody were to be, so if we were to take the last graph with the height and weight, if we had somebody who was 12 feet tall, how much would you think they might weigh? So now we're no longer using the data points that we have or values between those data points. We're moving beyond those data points. We're moving much, much further beyond that. And so we're having to use that to make predictions or infer values. We're starting to use that to figure out what we think might happen beyond that data set. If the values were the height and weights of just men, how do we think the height and weights of women? How do you think that graph might operate differently? Um, the same thing we could do with income, with weight, with whatever. We start to make inferences about, well, what do we think is going to take place with data that we don't have, or with data points beyond the data that we've already collected. And so this is a really important part about statistics, is that it gives us the power to start to notice patterns and then draw meaning from what we think might happen. Of course, it might not happen. Our prediction may be wrong, but it puts us in a position to be able to make those predictions. The reason I bring this up is because I think a lot of times people think about statistics and they think about this second and third level, which are complex for sure. And so if you think, well, kids aren't going to be able to do this level 2 and level 3, you might be right. I mean, they might be able to do some of 2 and maybe even some of 3, but there's a starting point of 1. And allowing students to work with reading the data and really getting a lot of proficiency with reading the data is what's going to get them to steps 2 and steps 2 and 3. So, when you start to work with your students and you start to get a sense of where they are, um, you may be doing a lot of 1, and that's okay if that's where they're at. And then when they're ready to move on to 2, level 2 here, or level 3, then you'll know, and you'll be able to do activities that are important and meaningful to them, that allow them to grow in their understanding of statistics. So, your checkpoint problem, here's a graph. I'm just giving you a graph. And what I want you to think about is, what can you tell me about this graph? What do you notice about the graph? What do you notice about the data? So anything at all that you can, any sort of meaning that you can draw from this that Riley seems to have done. So what do you notice about this graph? That's all. If you have any questions, you want to talk about what you noticed in this graph or anything else in this video, please by all means let me know. Be sure to ask in class and we'll get your questions answered. All right, thank you.